Okay, everybody, this is optimizations, the last lesson in this unit. And it's everybody's favorite word problems. So there are three types that we're going to look at here. The first one is basically a grade 11 problem. You could do with quadratics, but we're going to use calculus to do it. You have 70 meters of fencing. What is the maximum area you can enclose inside of a rectangle? I.e., what's the largest rectangle you can make? What are the dimensions? So first thing here is we're going to draw a picture. We know I'm going to call this x, this is y, that's y. All right, we have two formulas. Perimeter of a rectangle is going to be 2x, 2y. The perimeter in this case is 70 because we have 70 meters of fencing. So we have 70 is equal to 2x plus 2y. That's the first formula. Second formula is area. It's the thing we want to maximize. And that is the area of a rectangle is going to be length times width. So in this case, x times y. All right. We want to maximize this. So we need to take this equation, the perimeter equation, and solve for one of the variables and sub it into the area formula. So it doesn't matter which one you solve for. I'm just going to use, we'll solve for x. So it's 70 minus 2y is equal to 2x right off the 2's. So you get 35 minus y is x. That then it goes into there. You get a new equation. A is equal to 35 minus y times y, which is 35y minus y squared. That's our area. Now, this is good because we only have one variable in this equation, which is what we want. So now, if I want to maximize it, we need to take the derivative. So a primed or dA dy will be 35 minus 2y. We need to find the critical numbers. So we're trying to maximize it. It's just like curve sketching. So we set it equal to 0. 35 minus 2y equals 0. 35 is equal to 2y. Divide off the 2, and we get 17.5 is equal to y. Since we're meters, that should be in meters. So that's what we get for y, but we have to show it is a max. So prove it is a max. That's part of this whole gig. Prove max at y 17.5. There's two ways to do this. One is the first derivative test. And to do that, we mark our critical number, which in this case 17.5, and we just test the intervals. So if I put a number less than 17.5, it could be anything. Let's pick 0, because 0 is easy, into the first derivative. I put y is equal to 0 in there, I get 35, positive, increasing. If I pick a number greater than 35, say 50, into here, I'm going to get 35 minus 100, which means it's negative, so decreasing. Therefore, we know we have a max at y to 17.5. The second way to do this is, or you can use the second derivative test. Now, you don't usually use this unless it's a really easy thing to find a second derivative. So, second derivative, the derivative of this, the 35 goes away, the y goes away, we're left with -2. If the second derivative is negative, what does that tell you? Negative, therefore, on down critical point. So the graph will look like that. That would be 75. Essentially, the max. Doesn't matter which method you use, it's totally up to you. That's about as easy as they will get. Okay, so we're going to move to the second one here. Create create the largest open box with no top that is a square base and a surface area of 108 centimeters. Okay, so again, I always draw. Okay, so there's no top. It's a square base. So that means that I'm just going to use x's again. That's x, that's x. It's a square base. And we have the height. Okay. A box has a square base and a surface area. We want the largest, i.e. biggest volume. So what's the volume of a box? It's going to be x times h. So x squared h. That's what we want to maximize. We want to maximize the volume. But we have two variables here, x and h. We need to get rid of them. We have another piece of information, surface area. So surface area we know is 108. Essentially, that's how much material we have. And basically, the area of all the surfaces. Shocking, I know. So, the area of the bottom here is a square, so that's x times x. X squared plus the area of each side. So, if you look at this side has an area of x times h, as does this side, x times h, as do the other four sides. So it's going to be 4xh. Now, we want to solve for a variable. Here's our equation. We want to solve for a variable. The easiest variable to solve for is going to be h, because it's only one of them. So I am going to solve for h, and I won't write it in red anymore. Go back to blue. So I'm going to go 108 minus x squared divided by 4x is equal to h. So I rearranged it. This then gets subbed into that right there to generate one equation. Volume is equal to x squared minus 108 minus x squared over 4x. Alright, now let's simplify this because it's so fuzzy. This x squared on the outside will cancel that x there. Then I can multiply the x in. I'm going to get 108x minus x cubed all over 4, which divide out the 4 and you're going to get 27x minus x cubed over 4. That is our formula for volume in terms of x as one variable, which is what we want. Because now, since we want to maximize it, we want to derive it, just like we do in everything in this class. So v prime is equal to 27 minus 3x squared over 4. If you are going to maximize it, you need to set it equal to 0, i.e. find the critical number. So we have 0, 27 minus 3x squared over 4, and now it's just algebra. So 3x squared over 4 is equal to 27. Rearrange that, you're going to get x squared is equal to 36. So x is equal to plus minus 6. Clearly the negative 6 makes no sense. Therefore, 6. Alright. Show it is a max. Because we just have the variable. We need to prove that it is a max. So, x is equal to 6. Well, we'll do first derivative. Yeah, we can do first derivative or second. We'll do both. So, green. Blue. So the first derivative test would say v prime for a critical number of 6. Pick a number that is less than 6, so 0 is the easiest one. Put it into the first derivative, we get a positive 27. Number greater than 6, negative. So we're following, therefore, x equals 6 is a max. Or, or you can use the second derivative test. So if we take the second derivative, v double prime, again, it's pretty easy. The 27 goes away, 2 drops down, we get negative 6x over 4, which you could reduce to negative 3 times x. Okay, well, at 6, this is going to be positive, or negative, sorry. Which tells us we're concave down, which tells us we have a max. There you go. Oh, so now that we know that x is 6, how do we find h? So x equals 6. Well, you go back up here, use this formula right here. H is equal to 108 minus x squared over 4x. Minus x squared. Plug in 6. And that should spit out 3. Therefore, the dimensions are 6 by 6 by 3. You look at the box, 6 by 6 by 3. There you go. And I don't think I solved for This one up here, well, we have a max at y is equal to 17.5. X will just be 35 minus 17.5, which again is 17.5. So actually, it's just a square. Max area will be a square. That's a rectangle, but whatever. That is your answer. Sorry about that. All right, we have one more, last one. Color, let's do brown. You are to create a rectangular box with a square base from two different materials. The material for the top and the four sides costs $1 per square meter. The material for the base, the bottom, costs $2 per square meter. What are the dimensions of the box? All right. This box has a top. There we go. Okay. Square base again. I like my x's, so XX. That's H. Okay, so we're not talking. What are the dimensions of the largest volume? Okay, so again, the volume is our equation. Just like the last one, it's going to be x squared h. We want to maximize that. But we have a cost issue. Okay, so if we look at this, cost. Cost is going to be, so the material for the base of the bottom is $2 per square meter. Okay, so the area of this bottom is going to be x squared, and it costs $2 per that, so it's 2x squared as the cost of the bottom, plus material for top and all four sides. Now, the top, again, is a square, but the material is cheaper up here, right? It only costs $1. So, plus 1 times x squared, and that 2 is that 2, and that 1 is that $1. Plus the amount it costs for the sides. So the sides, again, we'll do it in a different color. This side, there's four sides. They have the dimensions XH, and they cost $1. And there's four of them, so it's $1 times the area, which is XH, but there's four sides, so put a 4 in front. Let's make that a 4 in there. 4XH. And the total cost is $144. So black. So 144 is equal to 2. Well, actually, I can combine that. Those to 3x squared. Plus 4xh. There is my cost equation. Again, we want to maximize the volume, so this is the formula we need to derive. So I need to get rid of one of these variables. Again, easiest to solve for h here. So if I go 144 minus 3x squared divided by 4x equal to h, and then that gets subbed into there. Now I have v equal to x squared 144 minus 3x squared over 4x. Again, it's a simplification game. That equals that. Then you can multiply it in. I got 144x minus 3x cubed. There, my volume equation, which I can rewrite or simplify anyway. 144 divided by 4 is 3 over 4, since we learned that's an actual decimal. I know I'm using decimals. I said no to. Be okay with it. There's our volume equation. Now it's a matter of deriving this to find the critical numbers. So v prime is equal to 36 minus 3 times 0.75 is going to be 9 fourths, which is 2.25. X set it equal to 0. So 2.5. X squared is equal to 36. Rearrange it, you will get x is equal to 4. Again, ignore the negative. Because when you square root something, you get a negative, but you're going to ignore the negative because that makes no sense. And that is our critical. Alright. Again, we now need to prove it. So I will ask you to prove it on your assignment. So you can use the first derivative test and mark critical number. You have b prime to pick a number that's smaller than 4. It doesn't really matter. Put in 0, it's the easiest one. Put 0 into there, I get a positive. So we're going up. Put a number bigger than that, I get a negative. So we're going down. X plus 4. Or you can do a second derivative test. B double prime again, the 36 goes away, and I get negative 4.5 x and at 4, this will be a negative number. So we are concave down, which means we have a max. Okay, so the dimensions. X is equal to 4. How do we find h? Again, using that 144 minus 3x squared over 4x. If we do all that, it should spit out the nice number of 6. So the dimensions of the box are 4 by 4 by 6. If you mark on the box, 4, 4, 6. Alright, that is it. I have some questions for you to do, some from your book, some I will attach. So from your book, you're doing page 12, 20, numbers 9, 11, and 19. Alright, and then I will also attach some questions and the answer keys. And that is it for this lesson, or for this unit. I will post an assignment early next week and give you some time to work on that before we start the second half of the course, which is integration. Alright, if you have any questions, please email. Thanks.